So, welcome to a discussion on the first test in the class in the course on signals and systems. I do hope that you enjoyed solving the problems on the test, and we now discuss the solutions to the test. Of course, I would say they are the instructor's solutions. Sure, they could be alternate solutions, and I encourage students to come out with alternate solutions. Let me take the solution to question 1 in the test. In question 1 in the test, you are given the impulse response of a discrete time system, and you are required to show that the current output sample can be related to the current input sample and a few of the past or future or current inputs. You are asked to show that yn can be related to the current input sample and a few of the past and or a few of the future input samples through a linear relationship. So, in fact, you are told that the impulse response is like this: 1, 2, -1 and half, respectively at -1, 0, 1 and 2. This is the impulse response, Hn. And you are asked to relate Yn with Xn and future. So, it could be Xn plus 1, Xn plus 2 and so on. And similarly past, so Xn minus 1, Xn minus 2 and so on. Now, you see, the idea is very simple. I mean, we make use of the idea of convolution. So, we realize that Yn is X convolved with H. Evaluated at n. But of course, we are at liberty to take either X convolved with H or H convolved with X. So, in fact, let us write both of them down. Now, we will prefer to use an expression where you have h of k and x of n minus k. So, let us write that expression down. So, we have y of n is summation on k, h of k, x n minus k. And from here, in fact, our job is done, because you have a finite number of non-zero h, and they will involve a finite number of samples of the input. So, we may straight away expand this expression. So, we have at -1, we have 1. So, 1 times x of n minus 1, which is n plus 1, plus 2 times x of n minus 1 times x of n minus 1, plus half x of n minus 2. So, this is the answer to the question. Now, in fact, this can be generalized, I mean, for any impulse response which has a finite number of non-zero samples. When you have a finite number of non-zero samples, the current output sample is a finite combination of input samples at some specified points. Let us take the solution to the next question, question 2. In question 2, the first part asks you to calculate the output of a linear shift invariant continuous time system given one input output pair. So, you are given one pair of input output functions as follows. You are told that this input produces this output. And of course, the system is LSR, linear shift invariant. You are required to find out the output corresponding to the following input. And this height here is 10 and this height is 5. This height is also 5, of course. Now you see, we of course, there can be various ways of doing this. But one simple way is to try and express this input in terms of this input and then use the properties of linearity and shift invariance. So the first step is to try and see if we can get this by shifting this input and adding it to the original input. So let me do that. So I take this input and I shift it. Let me keep this output as it is for the moment. I shift it by half. And that gives me an input. So here you are, this starts at half and goes up to 3/2. Now if I add this to a shifted version of itself by half, what do I get? I get this. So you see, what is the situation here? This is 2, this is 1. The situation is that we've got what we wanted except for a factor of 5. Now if I multiply, so what the input that we are looking for is this input multiplied by 5. Alright? Now we shall approach the problem in 3 steps. First, the step of shift invariance. If I know the output corresponding to this, I know the output corresponding to this because it would be this output shifted by half. So I can write down immediately the output corresponding to this dotted input, which I will draw right here. Let me reduce this scale, that will make it easier. So this dotted output corresponds to this dotted input because of shift invariance. Now we can make use of the property of additivity. So if I add this input to this input, the corresponding output shall also get added. So this solid input shall be added to the dotted input. And that, the solid output shall be added to the dotted output. Now you see that there again I wish to make a point about adding straight lines. You see, adding outputs like this can be done very conveniently if you remember that the sum of two straight lines, or when you add two straight line functions, the result is also a straight line function. And on a straight line function, if I identify 2 points, I have identified the whole function. So, I will divide this sum into a number of segments. You see, look at it. I can take the segment from 0 to half first, then the segment from half to 1, then the segment from 1 to 3 by 2, then the segment from 3 by 2 to 2, and finally the segment from 2 to 5 by 2. In the segment from 0 to half, I have a sum of two straight lines. This straight line is 0 and that straight line goes up to half. So, this just rises up to half. So, draw a smooth straight line going up to half there. Now, when I add these two straight lines, the terminal points are here, it starts from half and here it reaches 1 plus half. So, remember this is 1. So, 1 plus half, it reaches 3 by 2 here. So, draw a smooth straight line from here up to 3 by 2. Its slope of course is doubled. Now, look at this segment. In this segment, you go from 1 plus half again to 1 plus half. So, it's a flat segment which remains at 3 by 2. And then of course, we notice that in this segment as also in this segment is the mirror image of this segment and this segment is the mirror image of this segment. So, therefore, here we have a smooth straight line bringing us down to half and finally, a straight line bringing us down to 0. So, that is the overall output corresponding to the sum of these two inputs. That is additivity for you. So, that is not the end of the story. Now, we need to multiply by 5. So, we bring in homogeneity. So, the output shall also be multiplied by 5 and that is the end of the story. So, what is the output? The output is essentially this scaled by a factor of 5. So, 5 multiplied by 3 by 2 here, this reaches 5 multiplied by 3 by 2 here and this would have reached 5 multiplied by half here. Now, let us take question 3. In question 3, you are required to show, of course, here the arguments are for a continuous time system, but the same arguments can go through for a discrete time system. So, you are required to show for a continuous time system in part A that if the system is only additive, you are not guaranteed about homogeneity, then an all 0 input results in an all 0 output. So, let us reason out. You see, xt results in white. The system is only additive system. Yeah, the additive property is obeyed. We do not know about homogeneity. Now, if the system is additive, we can certainly write down xt plus xt results in yt plus yt. But if xt is the all 0 input, then xt plus xt is equal to xt. Which means the corresponding output yt plus yt or 2yt must be equal to yt for all t. But But if 2yt is equal to yt for all t, then the only possibility is that yt is 0 for all t. So this proves the part A of the question. Now let's take part B. Here you are required to show that if a system is homogeneous, just homogeneous, not necessarily additive, even so, an all 0 input results in an all 0 output. So let's take the situation. Suppose xt produces yt, the system is only homogeneous. Then because the system is homogeneous, I can write down 2 times xt produces 2 times yt. And by an exactly similar argument, I mean, if xt is 0 for all t, then 2xt is equal to xt. And therefore, the corresponding output 2yt must be equal to yt for all t. And this can only happen when yt is equal to 0 for all t. So it's clear that purely additivity or purely homogeneity are enough to guarantee that an all 0 input results in an all 0 output. But in part C, you are required to show that this is, not predictable. In the sense, either can happen when the system is not additive or not homogeneous. So let's take a system that is neither additive nor homogeneous. It's clearly nonlinear. Now we are required to show that it is neither. One cannot say with certainty anything. Sorry. Either it could be true that an all 0 input results in an all 0 output, or it may not be true. Let's take examples of both. So if we consider the system yt is equal to xt squared, it is very clear that an all 0 xt will produce an all 0 yt. But if I simply modify this system by adding 3 to it, so I have yt is equal to xt the whole squared plus 3, then the system still remains nonlinear. But now an all 0 xt does not produce an all 0 yt. In fact, yt is equal to 3 for all t, so it's not all 0. So for a nonlinear system, nothing can be said if the input is all 0. The output could be all 0 or it may not be all 0. I must emphasize one point here. You see, when we talk about this all 0 carrying over, it is all 0 that is important. That means an input which is 0 for all time results in an output which is 0 for all time. But because an input is 0 at a particular point in time, does not mean in a linear system the output must be 0 at that point in time. That is not what this question seeks to prove, or in fact that is not even true. So it's quite possible that an input could be 0 at a particular point of time and the output will be non-zero at that point in time in a linear system. That's point-wise. But here we are talking about all 0 inputs, meaning inputs that are all 0 for all time t. Now, in question number 4, you are given that x convolved with h is y. Right? In other words, if you have an input x on time and impulse response h on time, and the output is also on time, then there is this convolution relation between them. You are required to find out the convolution of x2t with h2t. So you are required to convolve x2t with h2t. So what is, I mean, we will work it out mathematically, but what is the aim in this question? The aim is to find out the output when both the input and the impulse response are squeezed by a factor of 2 in time, right? So let us work it out. You see, it is very clear that integral x lambda h t minus lambda d lambda is equal to y t. Now let us denote x of 2t, let us denote x of 2t by, let us say, g of t, and h of 2t by h1 of t. So what we are asking for is the convolution of g with h1, right? So that is integral g lambda h1 t minus lambda d lambda. Now you see, what is g of lambda? G of lambda is x of 2 lambda. And h1 t minus lambda is h of 2t minus 2 lambda. And of course, d lambda is as it is. Now here we can make a transformation of variable. Suppose we put 2 lambda equal to 5. Then what does this become? This becomes integral x of 5 h. Now please note, it is 2t minus 5, that is fine. It is 2t minus 5, not, so you must be careful. This 2t is 2t there. And d lambda of course becomes d phi by 2. So in fact, there is a neat relationship here. This can clearly be seen to be y at 2t divided by 2. Alright? This is an interesting relationship. What it says is that if I squeeze the input by a factor of 2 in time, and if I also squeeze the impulse response by a factor of 2 in time, the output is also squeezed by a factor of 2 in time. That means, it's as if you are speeding up everything by a factor of 2. But there is also a multiplying factor here. Alright? So that ends the test, and I do hope that you enjoyed solving the questions once again. If there are any other questions beyond what I have discussed as a solution to the test, or if there are any clarifications, we shall certainly be happy to entertain them the next time. So with this, I wish you all the best and look forward to seeing you in the next lecture. थोडंसं प्लेबॅक करून बघायचं का? ते मी थोडंसं बदलले क्वेश्चन, म्हणजे काय की ते ऑर्डरिंग बरं झालं एका दिवशी रेकॉर्ड झालं. Because in y1n plus y2n, you would require to have x1n plus x2n plus 6, not x1n plus x2n plus 3, and therefore the system is not linear.